Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue our discussion on linear models and look at generalized linear regression. Specifically, we'll look at what GLM is, that is generalized linear model, and look at the three components of GLM. Then we'll look at what are link functions and the associated cost function for GLM that needs to be minimized, and how the unit deviance is part of that cost function. Finally, we'll look at a slide on the code snippet before we get into coding in Jupyter Notebook. So why is generalized linear model needed? If you look here on the left hand side plot, we have a familiar linear fit where we have the on x-axis we have it could be a feature x, and then y-axis we have the response variable, that is the output y, and these orange dots denote the data points. And as you can see, as x increases, the value for y also increases. In addition, we can see that the spread of the orange dots right from here bottom left corner up to the top right, it's about the same, and it is shown by this green Gaussian curve that's overlaid on top of the orange plot. So that's what we usually have seen in previous videos with linear regression. Now, what happens is there are instances where the spread in these orange dots or the data points is not the same all the way across, as seen here on the figure on the right hand side, where we see that these dots are much closer together in the bottom left corner, and they tend to spread apart as they move. As the value of x increases, the variability seems to increase within these orange dots. As well as we can also see that the blue line that is fit to these data points, it's no longer a straight line. It has some sort of an exponential shape to it, because after a certain point, a small increase in x results in a rapid increase in the value of y. And the overlay of these blue curves show that the distribution of the orange dots is not the same across the entire data set. It changes. So these change in variability and the change in the dependence of x and y, which is not linear, can be modeled by a family of exponential distribution functions which come under generalized linear model. And here are some of the examples that we are going to see with scikit-learn. The very first one on the left is the Poisson distribution, where the values start from 0, go up to 10, and the plots, as you can see, have a tail on the right hand side. If you look at this orange curve, and at certain values, they also are similar to a normal distribution shown by this red curve. In the middle, we have the Tweedy distribution, and again, this distribution can be used to model when the response variable that's on the x-axis here has is distributed as shown here, where it has a heavy tail on the right hand side. And finally, we have the gamma distribution, which is the third plot, and it's also belongs to the family of exponential distributions. And we can see that these plots again have specific shapes that can be modeled with the generalized linear model. So the components of generalized linear model, if you read the literature, are these three random components. There is a systematic component and there is a link function. So the random component is basically the probability distribution of the response variable y, or the plots that we saw on the previous slide. And the systematic component is the linear combination of the features or predictor variables. Uh, we have been denoting them with x, and those are related to each other in a linear combination by beta in this case. For this, we have denoted this by W. So, for example, W0 plus W1 x1 plus W2 x2 and so on. And this particular xb equals to eta, and that's the linear predictor. Now the link function g is a link between this systematic and the random component that is shown here, and it is given by this equation down below, which is the expected value of y given x is equal to this inverse of the link function for eta. And the link function are shown in this table, where what they essentially do is they bring the values of the response variable within a range such as these for the type of distribution that you apply it to. So for normal distribution, the range would be minus infinity to plus infinity, and this would be the identity link as shown here. Xb is equal to mu. Then for Poisson and others, the range is from 0 to infinity, so only positive values. And as you can see, these are the link functions that can be used with these types of distributions. Now, Poisson distribution, as we'll see in the coding examples, generally used when you have a distribution where you're counting numbers. So maybe count of uh, defective parts from a machinery, or count of insurance claims that we'll see in the video over a specific time. And the link function, this is from the scikit-learn docs, which says that the predicted value of y hat given the parameters w with based on the parameters w and the input variables x is equal to this h of x and w, which is h is the inverse link function, and here w is the beta that we have seen before. And the cost function that needs to be minimized is given by this relation, where uh, the part that is new and different from the previous equations. If you remember the equation from ridge regression, it is similar to this, where here we have been using the sum of squares difference between the actual and predicted values, and this is the regularization term here for the L2 norm. And this particular part where it is d of yi and y hat I, that's the unit deviance, and that is given by these relations that are shown here in this table. So for normal distribution, that would be the sum of squares difference between the actual and predicted value square of those. But for Poisson, gamma and inverse, these are the relations that are used as scikit-learn this cost function. So with that, this is the code snippet, and the format is similar to what we have been seeing before. For the PD regressor, uh, we can set the value for power, and if it's set to 1, then we'll be working with a gamma Poisson distribution. It can be set to 2 or 3 or 0 is the default, and accordingly the link could be set to either auto or log to perform this fit on the trained data set, and then you have a prediction with the test data set. Now let's get into Jupyter Notebook and look at an example. I wanted to share this page from scikit-learn docs, which is the example that we are going to be looking at, and this is about French motor third-party liability claims dataset, and these are the authors Christian, Roman, and Olivier, and we'll be using the exact same code that's in this example. So if you want to, you can look through the uh, code that's in the docs and skip the rest of the video, or you can follow along with this video as I talk and explain the code and how it relates to the generalized linear model. So here I've imported a couple of libraries, including NumPy pandas and several parts from the sklearn, and these are the versions that I'm using. Now for the data set, that so for data set we are going to import the data from OpenML, and to get that the command is fetch underscore OpenML, then data underscore ID is equal to 412 and 4, and as frame, guessing that is for as a data frame is equal to true dot frame df dot head. We look at that, so should have the data frame listed below this cell in a moment. Once we have that, then we can look at what the data set looks like, and then we'll proceed next calculation. Okay, so this is the data set where we have these claim numbers, which are the insurance claims, and then these are the exposures, that's the duration for each of those insurance policies, and then these are other parameters that we need to take into account predict if that to predict the number of claims. And we can here we can also look at the general layout of the data by calling df.describe. So not all the variables here are numeric, even though they are new. For example, vehicle gas, that's categorical, region, vehicle brand, then area, those are all categories. Others are numeric. Now we also can do one thing. We have to create another new variable, and to create that variable we need to type in. So we'll create a variable called frequency, and to do that, df frequency is equal to the frequency of the claims. So df, and then here we have claim number and divided by exposure. Now if you look at df.head, we should have that additional column listed at the very last. So this is the column that we have created. Now what we can do is, because this is the response variable or the output variable or the dependent variable, we can look at its distribution and see if it's normal distribution or not. And as we have seen from the slides, that generally we want to use a generalized linear model when the distribution is not normal. Of course, you can use it with normal distribution. Link function would be different. So frequency, and here I'm going to use bins of 30. Then next thing, we want this to be on log scale. If we don't plot it on log scale, this is what we get. So if you want to pull the smaller values that are on the y-axis, and specify log is equal to true. So that's the distribution. As you can see, it has a heavy tail on the right hand side, and that's a good candidate for a Poisson distribution. Here we can look at claim number. Again, the same set. You can see this also has the same tail that we have been talking about. Finally, let's look at the exposure as well. This has a different type of distribution. Here it's almost flat, and after that it starts to drop down. There's a tail on this side. So with this in mind, we can now go ahead and start working our way through the rest of the code. Now, another important point to note in this particular data set is the uh, number of claims that are zero. If we look at df claim number and the df dot, or you can df dot lock, where df claim number is equal to 0, and if you look at the exposure column, that divide that by exposure sum, around 93% of the records have the claim number as 0. So it's a highly skewed data set. We can also look at the percentage again with df.log df claim number equal to 0. Would just get the sum of claim number, the count of those. Df claim number count, and you can see, so most of the values for claim df claim number would be 0. Just look at those. Most of them would be 0. A few of them would be non-zero. So dot unique. So there are some of them have 11 claims, 3, 16. Most of them are 0. Now to proceed, what we'll do is we'll create a pipeline. So what the pipeline will do is apply the transformations to the data set. So for example, standardize, lock transform, or do one auto encoding, and or binning. All that can be done using this simple single pipeline. So we'll first create a lock transformer pipeline. That log underscore transformer is equal to make pipeline, and this is going to use the pre-processing library. So pre-processing dot function transformer. Here we'll use the log np dot log read is equal to false, and then the second one is using standard scaler. So pre-processing dot standard scaler. So that's the one part, and then the second one is you will use the column transformer. If you do not remember that, we have discussed that in detail in one of the previous videos in this series. Linear underscore model underscore the processor is equal to column transformer. Here we'll specify a list of tasks that need to be done. So the first one, and I'm copying this directly from the docs as is with some modification. Pass through numeric, and this is the give name pass through, and the column name is bonus malus. and this column will just as is through this particular pipeline. The next one is create bins. So bin numeric. This will use the k bins discretizer here. Pre-processing dot k bins discretizer, and we specify n is equal to n bins. We'll specify 10 bins, and the columns that need to be binned are vehicle age and driver age. So what that does is it gives us a new categorical. We are creating categorical features from these two numeric columns. Then next one is log field numeric, and here we'll use the log transformer that we created above. And the column that will do the transformation of is the density column. So why don't we quickly look at these columns? df.head. So as you can see, the density column is this, and if we plot the density column, df dot dot hist df density, you can see that it's highly skewed. And now if you put a log transform on this, so np.log, and now you see it has more normal like distribution. So maybe that and the values for this particular column. So if you look at df density, if you look at the min value and the max value, so the min is 1 and the max is 27,000. So it's important that this needs to be scaled, and that's exactly what this log transform will do for us. Finally, there are categorical columns that need to be one hot encoded. So that one hot categorical categorical, and for this we'll use the pre-processing dot one hot encoder. Columns would be vehicle brand, so that's right here. Then we have vehicle power. It's numeric, but still we are going to convert it. We are going to, power is it is numeric, but then it is categorical. Vehicle gas, or type of gas. Then we have region, and we have area. Keeping now we have included vehicle brand, and for the remainder columns, just say drop. So those columns would be dropped. So with that, we have an error. So is n bins. Okay. All right. So with this, now we can use this to create our first set of prediction. The first one we are going to use is on a dummy regressor. I'll explain what that is in a minute. before we do that, even that need to split the data set. So we'll do that here, split it data set. We have df underscore train, df underscore test is equal to train underscore test underscore split, and this is going to use the data frame df that we have above. Specify the test size as 0.3, 30% random state is 0, so we get the same records. Okay. So the dummy is equal to pipeline. Here first is preprocessor. So preprocessor, we have linear model dot linear underscore model underscore. That's what we created above. So it'll pass through that, and then once the data set is uh, rearranged, scaled, formatted, and ready for the fitting, we'll then enter this part, regressor, and so we are going to use the dummy regressor. I think we have ported, yes, that's the dummy regressor, and strategy to, so we'll pass that, and then we'll fit it for dummy dot fit df underscore train, df underscore train. Here we have frequency is this is the x, and then we have the y. Here we specify regressor underscore sample underscore weight is equal to df underscore train, and then specify the weights from the exposure column. Okay, so there is an error, not enough values done tag. Got to, so finally figure out the error is because I have an extra parenthesis here. I want to remove that, add that here. When we run that cell again and run split and then run this, we get this working. So after that, let's move on and look at the next step. So for the next step, we are creating a function to calculate the core MSE and MAE, so mean squared error and mean absolute error. To do that, create the function here, scoring. So df core estimator. Here estimator is what regressor we are using, then apply it with the test data set. Here we first create the prediction, so ypred is equal to estimator dot predict, that is based on the test data set, so df and test, and then we can calculate the mean squared error and the mean absolute matrix dot mean underscore squared underscore error, specify df underscore test, specify frequency, specify y underscore pred, specify the sample weight, so sample underscore weight underscore equal to df, and this is will be df test and would be based on exposure column. So df underscore test, then specify exposure, round is to 2 decimal, put a 2 there, copy this exact same column, paste it here, and this could be for MAE. So we'll change the square to mean absolute error, and the rest of the line stays the same. And after this, you can go ahead and print those values. So print MSE is equal to this, then print MAE is equal to this. Once these are printed, there is also one change that we need to do is ignore the values that are negative uh, after they are predicted. So ignore negative predicted values. So to do that, here we are creating a mask where y pred is greater than 0, so only positive values. And when we create the matrix, so matrix dot mean underscore Poisson underscore deviance df underscore test, again frequency, and we'll apply the mask that we just created so that only positive values are considered. Y underscore pred, apply mask, same mask to that, then finally apply sample weight equal to df underscore test, and here we apply, use the exposure column with mask applied to it. So mask, then round out all the values, so round to 2 decimal places like so, and finally print the values. So print mean Poisson variance, and this is MPD. So that's the function that will do the calculation for the scores and print them out. Here I'm going to call that function. So print constant mean the calculation by calling score estimate. Dummy is the regress estimator that we are using, regressor, and then the data set, which is the test set. So those are the values we have. Next, we'll look at ridge models. So for ridge, we'll use the same pipelines. So ridge underscore GLM is equal to pipeline, and within this we can specify first the preprocessor, and that is going to be the same linear underscore model underscore preprocessor we have created above. And next comes the regressor, which is linear underscore model dot ridge, and here we'll specify the value of alpha equal to 1e to the power 6, and then use that for fitting. So ridge underscore glm dot fit df underscore train df underscore train. Here this is the y value frequency. Then we'll specify the weights, regressor underscore sample underscore weight. This would be equal to df underscore train column exposure, exposure. Okay. And then finally we'll go ahead and print the value. So print ridge evaluation, and we'll call the score underscore estimator and specify ridge underscore glm as the estimator and ef underscore test for test data set. And these are the values, and they're fairly close to what we had above. Now, beyond this, we'll now look at the Poisson regression. So these would now take into account what we have been looking for, which is the deviance from the normal distribution of the response variable y. Here, let's use Poisson regressor, and the code would be the same as here. So I'm just going to copy that, change these names, Poisson, and this again, this part would be different. So that this is going to be Poisson regressor, and here we'll specify alpha is equal to 1 e to the power minus 12, saturation is equal to 300. Then again this name changed, so we change this to Poisson, and again the final printing part on, and this. Okay, so I think we are good. We have the pipeline setup, we have the fit on train, and core estimator is using this particular variable Poisson GLM and with the DF on, and this should give us the values again for the MAC and MAE, as you can see values. Then we'll also go ahead and create similar evaluation for 3D regressor. So 3D regressor, and for this copy the same stuff, change this to 3D, and again change this entire part to 3D regressor, and set the power equal to 1 and link as log link. Then go ahead and change this as well. So 2D, rest is the same. Change this to 3D, this to 3D. Okay, so we have the variable name changed. Then we have the regressor set, and we fit. Finally, we are printing this. This is using the 3D regressor, and beyond this, we can also look at another variation, which is the gamma regressor. So for gamma regressor, that gamma regressor. So for gamma regressor, we need to do some changes. So talk about those. N samples is equal to so I'm going to create a copy. XX is equal to df underscore train dot copy. The reason why I'm creating a copy is because I'm going to change the values of the column frequency wherever it is 0 to a very small value close to 0. np.where df underscore train frequency this is equal to 0, 1 to the power minus 15, df underscore train, else just keep the values as they are. So that's that. Then repeat the same thing for the test. So call for the test, calling this as xt. Again, change this to df underscore test. Change this to df underscore test. Okay. So the reason why I'm doing that is to avoid an error. Gamma underscore glm is equal to pipeline, and then we need to specify the exact same stuff. Copy this, typing gamma underscore glm, and then this part would be changed. I'm going to just type gamma regressor, and this would again be gamma, this would be gamma, this again would be gamma, and the rest of this is the same. So if the reason, so what I'm doing here with the np.where, so np.where, you look at the help menu, it this is the condition where x and y, so it is, if it is true then this, if it is false then do that. So your condition boolean where true yield x, otherwise yield y. So if if it's true then yield x. So here we have, if this is equal to 0 then substitute it with a value of 0.0000, 16 zeros and 1, else substitute it with the value that's okay. So now we can run this, and some of the values are out of, so the reason for that particular exercise here was to avoid that error that is here, and the reason why that error still exists because we did not use the values that were changed. So now when we run this, error should, and so these are the values we get for the gamma regressor. Now after gamma regressor we can now look at the predictions, combined predictions of the total number of insurance claims. So let's call this section as predictions, markdown, and for this again we'll go ahead and create another function, is mean underscore frequency, and this takes in the true value for the response variable and then predicted values, and again the sample weight we can specify it. So here this is initialized to none, and the number of bins. So the idea here is that we bin the data set for the response variable and then do the count on that. So for first step is to sort it. So index sort is equal to np dot arg sort y underscore pred. We are sorting the predicted values. Then bin centers is equal to np dot a range. So from 0 to 1 divided by n underscore bins. So this part later is, well, we can create the bins way we want, but I'm going to follow what's in the box. 0.5 underscore divided by n underscore bins. Then y underscore, we initialize the y pred y true bins, y underscore pred underscore bin is equal to np dot zeros. in bins, then again y underscore pred y underscore true and true underscore bin is equal to np dot zeros n underscore bins. After these are initialized, now we can use the for loop to get the averages. So n for n and s in enumerate, here using the function gen underscore even underscore slices. So generate even slices for length y underscore true and underscore bins. So we have weights is equal to sample underscore weight sorted index, then use the s from the enumerate y underscore pred for bin, then for that text we have put in the average value n dot average y underscore pred text underscore sort s weights is equal to weights which we have above. Copy this and then here the second one is for the true value, so that this would be true, the rest of the code will be the same. Finally, I want to return bin underscore score centers y underscore true underscore bin y underscore pred underscore bin. Okay, so with this we are now ready to calculate the predicted claims. You can go ahead and print actual number of claims. So actual number of claims, and this would be equal to df underscore test claim number. Let's do the sum of that for the predicted values. Again loop through all the models. So model in, so we have ridge underscore glm, we have Poisson underscore glm, FPG underscore glm, we have gamma underscore glm, and finally we have dummy. For each of these we have y underscore pred is equal to model dot predict. We are calculating based on the test set, so df underscore test, and then y underscore true is equal to df underscore test. So these are the actual values for the frequency, and create values becomes array. Exposure is equal to df underscore underscore test exposure, again values. These can then be input to the function above. So mean underscore frequency, and this takes in y underscore true, y underscore pred, sample underscore weight is equal to exposure, and in number of bins we are creating 10 bins here, and the output, so it's going to return three values, so we need to create three variables for those. So q y underscore true segment, and then y underscore pred segment is equal to this. With that we can print the output. So print predicted claims. Here we have model, specify the model, and then format np.sum y underscore pred exposure, and this. So these are the values we get for the predicted claims or insurance based on different regressors, and the actual claims are 11,935, and we can see that the ridge regression, uh, because it cannot account for the age and the distribution that y has, the output has, it is underestimating the actual number of claims by big margin, by almost 1,000 less. Here 10,10692. However, if you look at the Poisson and the gamma regressor, sorry, Poisson and TD regressor with power of 1, so that's again Poisson, we get values that are fairly close to what the actual number of claims are. So 11,935 is the actual, and we are at 11,931 and 933. The gamma regressor is much lower. Maybe if it is fine tuned, it will give higher values. But then we are looking at count. So the optimal regressor to be used in this case is the Poisson regression, which is doing better. Now the dummy regressor, again, we use the mean value, and it seems to be good at guessing the mean for the population. So it is closer to actual number of claims are. So that was it for this video. I hope in this video you at least got some intuition about what generalized linear models are, what is a link function, how it looks, and what is the objective function that we are trying to minimize when we are implementing generalized linear model in sklearn. Finally, we looked at the implementation using the insurance claims examples from the logs, and we saw firsthand how the Poisson performs much better in predicting the number of insurance claims as compared to the ridge regression, um, that that does not account for the uh, shape of the response variable y, in this case frequency that we have seen, which has a heavier tail on the right hand side. I hope this video was helpful to you. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video. Please like, share and subscribe. Thank you.